Hey Algebra 2 and Honors Algebra 2 kids, it's your favorite math teacher, Mrs. Fellon here with another riveting video on, I'm actually going to do 4.7, 4.8, 4.9 kind of in one big video. It's actually not going to be that big of a video because we're skipping some of the stuff. So anyways, what we're going to be talking about here, and I'm kind of starting with the very top of this. So we're going to kind of jump around a little bit. So I hope that doesn't, throw anybody off. But anyway, what we're going to start with is I'm on page 113 of your student journals. And we're going to start talking about local mins and local maxes. And I'm actually going to introduce you to some other vocab word, even though it's not on here, we're still going to talk about it. It's called global mins and global maxes. All right, so I'm going to draw two little, it's easier to do this by picture than it is to do by like definition. So I'm going to start by drawing two grids, and I'm going to draw in a couple different types of graphs. So I'm going to do something like this for this one. And maybe for this other one, I will do like a cubic. Something like that. Okay. So first I want us to kind of talk about this idea of increasing and decreasing. So what you're doing is if you were starting to draw this function, right? This is how I kind of think of it. You would start down here and you would draw up. So this is kind of where your function is increasing. All right, then you get to the max where it's kind of even, and then you start going down the hill here, and this is where it's decreasing. And so ultimately there's multiple times throughout the course of a parabola, or not parabola, but a polynomial function, where your function is either increasing or decreasing. So this would be increasing, and this would be decreasing. And so what we're looking at here is for you to go ahead and kind of just understand this whole idea of like when it talks about the function as increasing or decreasing. So you would say something like, let's say this was at the point, we'll just make this up. Let's say this maximum here is at the point -2, 5. So you would say this function is increasing from -infinity to -2. It's decreasing, and let's say it's decreasing. Let's say this point is at the point 3, -2. So it's decreasing from when x is -2 to when x is 3. And then likewise all the way through. So you're kind of describing where it's increasing and decreasing. So I know in Big Ideas, they kind of talk a little bit about that. They give you some parameters. And that's ultimately what you're talking about, is where are the x values, for what x values is the function increasing, and for what x values is the function decreasing. So again, like on this one, because we're starting at here, like again, if you were going to draw this, you would start here and move down. So this means that your function is decreasing. And then here is where your function is increasing. And then likewise down here is where it's decreasing again. All right, the other thing I want to mention is this idea of something called a local min, local max, and then we're even going to throw in global min and global max. So what I mean by that is, let's start with our even polynomial. So this is an even degree polynomial. I know that because both of my ends are pointing down. This is an odd degree polynomial because both my ends are pointing in opposite directions. So for an even degree polynomial, you can have multiple maxes or multiple mins, depending on if your function's opening up or opening down. So notice that I have two maximum points here, okay? We call one of them a local max, and we call the other one a global max. So here's the difference between the two. A local max, you can have multiple local maxes. So think about a function that has lots and lots of terms, okay? So I'm just gonna make one up here. So let's say I had a function that did this. All of these, this would be a local max, a local max, a local max. What makes a global max special is it's the ultimate max. So it's kind of like, like in quadratics, we had a min or a max because there was only one, so you couldn't have more than one. Well, here we would have a local max, a local max, a local max, and a global max. That means that's the highest maximum. Same thing goes if it was a minimum, right? You'd have your local mins and your local maxes, same deal. Notice that this function, so it goes up, comes back down, goes up, comes back down. This is a minimum here. We're going to call this a local min. The reason I can't call that a global min is because there is no global minimum. This is a function that's decreasing forever. It's going down to negative infinity, which means there is no ultimate minimum. You can have many local minimums, but you're not going to have a global minimum on this particular function. So the biggest thing I want you to understand is that we have local mins and local maxes and global maxes. So the local is kind of like multiple ones, so you can have any kind of maximum, but the ultimate maximum point would be your global. And then for local min, same deal. I can't have a global, I can't have a global min because of the fact that the function's decreasing forever. So there's only a local min. So that works with even degrees. With odd degrees, there is never a global min or a global max. And the reason why is because of the end behavior. One end points up, one end points down, which the function is always going to infinity and negative infinity. There is no ultimate minimum or ultimate maximum. So all of these, so this would be a local max, and this would be a local min. So like for comp books and stuff, I don't really need you to get into super big detail. What I'm really looking for is for you just to kind of, you know, like a diagram, kind of understanding the difference between the two, talk about increasing, decreasing, that kind of thing. All right, let's talk on page 114. So I'm just going to kind of walk through a couple of these. So on this one, it says the turning points of a polynomial function. The graph of every polynomial function of the degree n has at most n minus 1 turning points. All right, so I'm going to graph some functions for you, okay? So I can explain this concept. So if I have a quadratic, or good old parabola, and then I have a cubic, and then how about I have a quartic, okay? What they're getting at here is you can also determine the number or the degree of your polynomial by the number of terms in your polynomial. So for example, in a quadratic, we go from decreasing to increasing. That's a turn. So there's one turn. This means that my degree, so if the number of turns, so if the number of turns is 1, then my degree is 2. So basically what I'm getting at is the number of turns is 1 less than the degree. So here, I start down here, I turn. Basically, anytime you go from increasing to decreasing. So here's a turn, here's a turn. So I have 2 turns. So the number of turns here is 2, which means my degree is 3. Why this is helpful is if you have a graph and you're unsure about like the degree of the polynomial, if you count the number of turns and just add 1 to it, you should be able to figure out the degree. So see how this has 3 turns? This means my degree is 4. So the number of turns is 3, my degree is 4. That's what that theorem or that rule states. It's just kind of talking about like the number of turns on a graph. I thought that was worthwhile to note. Okay, so a couple other little things. We're not going to get into this too much, but I thought I'd mention it just for fun. Even degree functions, odd degree functions, right? So one of the things they talk about is an even function is symmetric around the x-axis, or the y-axis, I'm sorry, I misspoke. And an odd function is symmetric around the origin. So what they're getting at here is this is like, so if it's truly an even function, this would be symmetric around the y-axis. If this is truly an odd function, then it'd have to be symmetric around the origin. So we don't really get into too much about the evens and odds, and so I'm not going to get into a whole lot, but I just kind of wanted to get into at least kind of recognizing just the lines of symmetry. And this doesn't work for all of your functions. So this only kind of works if your function is considered symmetric around the y-axis, then we consider it an even function. If your function is symmetric around the origin, then we consider it an odd function. All right, moving right along. I told you we were going to jump around a little bit. All right, I'm on page 117. So what we're getting at here is how we can determine, and we've talked about this in the last unit, but how we can determine the type of function just by looking at the set of differences we have in a table. So a lot of times this comes into play when we have kind of a modeling situation, right? So it's not just like, here's an equation, here's a situation that describes something. So what I wanted to get at here is if you find, so do you remember what we talked about in the last couple videos? If the first differences are the same, that means it's a linear function. If the second differences are the same, then it's a quadratic function. So do you remember us saying that, right? So if you look at this one, here's my, so we notice that the x values in my table are all increasing by a constant rate. So as long as the x's are increasing at a constant rate, when we do the differences, we're looking at the y values. And so they just kind of put them here. And so if you subtracted 220 minus 194 is 26, 247 minus 220 is 27, and on down the line, 29, 30, 31, 32. When I subtract these, I get 1, 1, 1, 1, 1. These are my second differences. So by having my second differences all constant, I know that this is a quadratic equation. Now, why is that useful? Well, number one, it tells you what kind of polynomial you're dealing with, but also when you're doing the regression, you know what kind of function to use. Some of you got confused on that when we talked about like linear versus quadratic regression. So you look at the second differences and you say, okay, well, it's supposed to be quadratic, so therefore I'm going to use a quadratic regression. So it says here, if we're going to do this problem, it says use a graphing calculator to draw a scatter plot. Does your data appear linear or quadratic? And so it's really hard to tell on this one. There is a curve, but it's really hard to tell. Use the regression feature of your calculator to find a linear or quadratic model that best fits the data. So because the second differences are the same, we know it's quadratic, and therefore I would use a quadratic model. And so when I did this one, you can check it by putting those into your table in your graphing calculator. This was what I got as my quadratic regression model. So I'm going to use this, and then it says, use your model in part B to find the distance a baseball travels when it hits an angle of 35 degrees and travels at an initial speed of 120 miles an hour. So I'm just going to start with that equation again. That's the one I found on my graphing calculator just by doing a quadratic regression. So I want to show you what you're doing here is you're saying, okay, so 35 degrees, that actually has no bearing because that was part of our original question. I don't know if you read it, but basically it said the table below shows the distances a baseball is hit at an angle of 35 degrees. So we don't really have to worry about that part, but the part I want you to pay attention to is the 150 miles per hour. So does the 150 miles per hour, does that your X or your Y? So if you're confused, you go back to your table. Which variable are we talking about? Well, miles per hour are your X's. So what you're going to do here is you're going to plug in 120 in for X. And obviously you have a graphing calculator, so you can, put this into your calculator. You do the math here, and I will tell you that you get 430 feet. So that's going to be so to go back to our thing, that's going to be the distance the ball travels if you hit it with that kind of velocity or that speed. This one says, according to the almanac, any drive over 400 feet is noteworthy, and below a below of 450 feet shows exceptional power, as a majority of Major League Baseball players are unable to hit a ball that far. Anything in the 500-foot range is generally historic. Estimate the initial speed of a baseball that travels a distance of 500 feet. So this one, you're asking for something different. You're actually now giving you your Y value. And so now what you're going to do is you're going to take your equation and you're going to solve for Y. I'm not going to work through this whole thing just because I know that you guys can do this. What I'm looking for you to do here, and I'll just do this part, but in order to solve this, you're going to subtract 500 from both sides. You're going to put this into your quadratic formula. So go ahead and do this. Remember I told you always leave your answers in reduced radical form with the exception of when you deal with a story problem. So you should get 130.14 miles an hour, and then because it's quadratic and you're going to get plus and minus, you're going to get negative 225.14 miles per hour. But then you're going to say to yourself, well, that doesn't make any sense because I can't have I'm not going to hit the baseball negative 225, miles per hour. So I'm going to go ahead and use this as my answer. get at here is this idea of making sure you understand. So we did the quadratic one, right? So now what I want to do is I want to extend our understanding of what we call finite differences. So I just wrote down, first differences, second, third, we're going to do a fourth, and then when they're the same, what kind of result do I get? So what I'm looking at is when the first differences are the same, remember this is when you get a linear function. When the second differences are the same, this is when you get a quadratic. Anyone want to guess this is what you get when you get a third differences are the same? I can hear you all the way from here. It's cubic. And then quartic. And then dot, dot, dot. In other words, it goes on forever. So what we're referring to here is they have to be non-zero and x's have to be equally spaced apart. So in order for this to work, the second differences have to be the differences have to be non-zero. In other words, you can't have, if all the differences are zero, then this pattern doesn't work. The other thing has to work is that your x's have to be equally spaced. All right, I'm making up my own example for this next one. And it's basically having you solve for an equation. So I'm going to ask that you write this down. So this is my example 1. And it says, find the equation of the polynomial that passes through the point and I give you the point 0, -12, and has X intercepts of -1, 0, 2, 0, and 3, 0. All right, so why I'm doing this is because I want you to be able to write an equation of a polynomial without having to look at a graph, okay? So first of all, I shouldn't have to tell you that those are x-intercepts, but I did. If you see a point like this and this and this, those are all x-intercepts, right? Because the y values are, well, they're 0. Second thing I want you to notice, if it has 3 x-intercepts, then we are talking about a cubic. So when you do this, ultimately what we're going to be doing here is we're going to be solving for a. So this is where we're going to be more specific into terms of our equation, not just talking about where the zeros are of our equation, but also talking about like our initial value or our a value, that initial value out in front. So I just turned all of my zeros into factors. So again, kind of like taking the opposite. There was no doubles or triples or anything. I'm going to plug in this point. And so it doesn't really matter what this point is. I gave you the y-intercept, but I didn't have to give you the y-intercept. And so what I'm going to do here is now I'm going to solve for a. So I get -12 equals 6a. So I get a to equal -2. Now I'm going to go ahead and rewrite my equation with my a value in front. So this is a specific answer, because remember when I said that there are infinite number of answers sometimes when you have like the same x-intercepts. This is the only equation for the line that passes through, that has those x-intercepts or those solutions, but also passes through that point. That's rather important. Okay, keep going. Let's do some others. Turn to page 120. I'm going to do a couple of these and save some for you guys to do because I don't want to do them all. Let's look at number 2. So number 2 says, write the function whose passes through the given points. All right, that's good. It has an x-intercept of 0, 0 and an x-intercept of -2. Well, if I only have 2 x-intercepts, I'm missing something. So what I want you to recognize is that this one's a double because it bounces off your graph. So when you write your equation, here's your x, that's 0, and x plus 2 need to be squared. So the x here represents this 0, the x plus 2, that factor represents this 0, and I squared it because of the fact that it's a double. My leading coefficient should be positive. How do I know that? Because of my end behavior. So now pick a point. So they gave you -3, -3. Plug it in. And solve. So I get -3a times, what is that, -1 squared. So that's just 1. So I get 3 equals negative 3a. I get a to equal negative 1. So my final equation is y equals negative x plus 2 squared. And that's how you solve an equation. Write your equation, I should say. All right, let me show you another example. Let's scroll all the way down to number 6. Number 6 is a table, if you hadn't noticed. It says use finite differences to determine the degree of the polynomial. Then use technology to find the polynomial function. Okay, great. So what we're going to do is we're going to go ahead and check to see that my x's are indeed increasing at a constant amount. And then I'm going to go ahead and do my first differences. So 4 minus 30 is negative 26. 0 minus 4 is negative 4. 0 minus 0 is 0. And negative 14 minus 0 is negative 14. All right, negative 4 minus negative 26 is 22. So I'm going to keep going until I see any that are common. 0 minus 4 is 4. Negative 14 minus 0 is negative 14. Watch all your set negative signs because you mess one of these up and it makes a difference. All right, still don't have anything common, so let's keep going. 4 minus 22, negative 18. Negative 14 minus 4, negative 18. All right, finally, my third differences are the same, therefore it's a cubic. So now what you would do, you are going to write the equation of your line, and it says you can use technology. So what you can do is you can go ahead and plug this into your calculator, you can plug in the table, and you can go ahead and write your equation. Let's see here, I have 2 X intercepts. I don't think I could do it by hand. So anyway, what you're going to do is you're going to type this into your calculator, type in your X values and your Y values, and you can generate a table or generate an equation for that. And so I got the equation f of x equals negative 3x cubed plus 2x squared plus x. All right, the rest of these are kind of done the same exact way. All I'm really looking for you to do is to use their finite differences to identify the type of function, and then you would just plug it into your calculator to generate the equation. All right, if you have any questions, bring them to class. Bye for now.